Okay, today we're going to look at flow over cylinders and over spheres. Now this is a little different than we've done before, and there's no theoretical preparation for this. We're just going to look at the empirical correlations which are contained in Table 7 in your book. We're going to give you some of the background on how these, on how the flow occurs over these different geometries. And the first geometry we're going to look at is the flow over a cylinder. Now, we're talking cross flow over a cylinder. That is a pipe in this direction and the flow going over it, not along the long axis. So, the first thing that we need to understand is the correlations are based on empirical correlations are based on empirical or experimental methods. There was a period of time in the not so much the 40s, but certainly the 50s, 60s, and 70s that a lot of PhDs were granted by people studying different geometries and developing correlations for heat transfer from those different geometries based on non-dimensionalized parameters of the geometry as well as the fluid properties of the flow. A lot. And to understand flow characteristics, you have to understand the following. Now, if you've already had fluids, you should call some of this, and if you haven't, or are taking it right now, you've done Navier-Stokes, right?
Yeah.
But you have you gotten a flow over cylinders? Okay, well, then you're getting a head start. All right, we're going to talk today about the forward stagnation point. We're going to talk about the pressure gradient. We're going to talk about the separation point. And boundary layer transition. Let's take a look at the slide. All of these pictures are in your notebook or in your textbook in chapter 7. All right. The first picture is of a cylinder, circular cylinder in cross flow. So the cylinder is running this way, perpendicular to the board, and the flow is going over it, as you see right here. Okay? Now there's a couple of interesting things. As the flow comes in, and these lines represent your stream lines. Okay? As the flow comes in, it curves around the body. Now what does it have to do as it curves around the body? Pardon me?
It just like goes around, so it goes its flow, like it changes its path.
Well, it does change its path, but what happens to its speed?
It slows down.
No, it speeds up. So it goes around, it speeds up. All right, it's got further to go. So flow that's down here from going to here is going at some distance and going at some velocity. But the flow from here comes in, it's got to go around, speeds up. Now that's the whole purpose of lift on an aircraft wing. All right. Now most of the time, aircraft wings are asymmetric. All right, so here's your typical aircraft wing. That's a bit of an exaggeration, but you get the idea. Okay? So flow comes in, and it goes like this. So, the flow on the bottom of the aircraft wing, this is an asymmetric aircraft wing. Airfoil is the appropriate name. So, for an asymmetric airfoil, the flow has further to go over the top of the wing. It goes faster. What happens to its pressure? It increases. Bernoulli's equation. So, what do you get? Forces acting underneath the wing, pushing it up, and that is called lift. Now I got it. Here's something for you.
But why can airplanes fly upside down then?
Why do some airplanes have symmetric wings?
But then one side's not longer than the other.
What about a wing like this? Okay, symmetric wing. What do we do? What do you have to do to have a symmetric wing fly, Austin?
You need angle of attack.
That's right. You need a different angle of attack. An asymmetric wing can have a zero angle of attack and be fine. But with the symmetric wing, you need some angle of attack. So in other words, you've got to tip the wing so that it's cutting into the air. So what happens? Same effect. If this is your symmetric wing, it's got to have some angle of attack here. So the air is going to come in like this and going to flow like this. So you get the same effect. And planes that fly upside down, there's several different things that go on. And that gets a little more complicated. They could either tilt their wings so that they're getting some lift off the wing in a new configuration, which is the typical way they do it. But that's the bottom line. You're going to have some lift,
Yeah.
unless you happen to be.
It doesn't come from a difference in length between the top and the bottom of the wing.
Well, that's what an asymmetric airfoil is. An asymmetric airfoil, it's got further for the air to travel over the top of the wing.
But the streamlines from the top and the bottom, they don't have to, the pieces of air don't have to get there at the same time. The back.
You don't, in general, have a discontinuity, and you don't violate the continuity equation. So if you draw a boundary around it, the particle of air that's at this point is going to be at the same point, in relatively speaking, at some delta t. So the bottom line is, the air doesn't slow down. It speeds up, or it could slow down, I guess you could say. But it's all going to be at the same time. It's going to be at the same place that it would have otherwise been had it not been disturbed. Okay? That's the whole point. If you don't have a difference in the velocity of the air, you're not going to get lift. I may not be explaining that right from your face, but in any case, what do we have right here on an aircraft? On the airfoil. That is the stagnation point. That's the same thing as you have on a cylinder. What happens at the stagnation point? The air just kind of stays there. It's a little air that's right there. It's not moving. So there is this point right here. So as the air flows over, above and below, we are forming a boundary layer on the surface. Now, at some point, what happens to the boundary layer?
Turbulence.
It begins to unadhere from the surface. There's not enough energy in the flow to keep it following the contour of the cylinder. And so you get this, well, you get a pressure differential here, and we'll talk about that in a moment. And you end up with flow coming back in here and creating turbulence. And at that point, the boundary layer is separated. On an airfoil, if your angle of attack is enough, what you do is the boundary layer pulls away. And when that occurs, you get the separation in here and you get the wake, and that is called stall. And that's a bad thing. And when stall happens, you have little, well, before stall happens on aircraft, you have warning mechanisms, beepers or lights in the cockpit which are saying you better reduce your angle of attack. Now there are some planes that essentially don't stall, some military aircraft. Now why is that? Because essentially rockets. Okay? So you don't need, you don't really need to worry about lift, you can just go straight up. Okay? But that's kind of consuming. You don't get great gas mileage when you're in that mode, but it does work for you. It's not so much, now
Different types.
yeah,
It's the
go ahead,
flow.
Scott.
The flow stalls, like the airplane just starts falling like a rock.
Yeah.
So it's not like your engine is shutting off,
Yeah.
like stalling a car. It's that the wing is stalled out.
Now you've lost your lift. Now, I think sometimes in the old propeller planes, they used to actually have the propeller stall. But I don't know about the jet aircraft. I mean, it doesn't happen very often. I think it's more of a phenomenon typically for propeller planes. I mean, anybody can stall, don't get me wrong. But what would happen is if the plane, if the engine did go out in an old propeller plane, it could sometimes tilt the plane over and dive, and the propeller would spin and be enough to turn the engine over. Sort of like taking your car. Any of you have ever had a car that's hard to start and it goes down a hill, push it. Not anymore. Nobody does. Have you had to do it? All right, well, good. All right. And it worked. Yeah, pop the clutch. Yeah. The problem is that you're not really supposed to push cars automatic transmissions. Yeah. If it's a manual, it's a different thing. You pop the clutch. Same sort of idea. If your engine would conk out in an airplane. All right. So this is what we're dealing with. What do you think happens in the heat transfer here? It's not as good as the heat transfer typically. Okay. You can, there are some exceptions to that statement, but here's another way of looking at what's going on. I told you that we had a pressure gradient. You can see the flow in the boundary layer. This is the boundary layer curve. What happens as the flow is beginning to transition and reverse is you'll see that the curvature of the velocity profile change, and then all of a sudden you'll see it actually reverse at the base, at the contact with the surface, as the flow begins to become turbulent and flow backwards.
Happens on the edge of rivers all the time.
Hedges on what?
Edges of rivers,
Yes. Yes.
they escape the current and move it the other way.
Right. I have thought about river flow, and you got to be a little bit careful to necessarily say it's exactly the same phenomenon as it probably is.
Especially
Because you're talking boundary layer theory here, and boundary layers are very, very thin. What you're seeing on a river is a macroscopic change. So, but at least on the surface, I agree with you, it looks like the same phenomenon. Okay, now if we take a look at this ball, or this cylinder, we have formation of a laminar boundary layer, and what typically happens with the laminar boundary layer is there's not enough energy in the boundary layer to adhere to the cylinder. So with a laminar flow, you get separation at an earlier angle than you would if you had a turbulent flow. So turbulent flow with more energy keeps the boundary layer adhered. And we've already talked about that on an airfoil where they typically, you can see it on commercial airlines where they rough the surface of the wing.
So like a golf ball, how they have the
That
holes
is
in it?
another excellent example of why the surface is roughed, to create a turbulent boundary layer so that the air adheres to it better. You get a better flight. There are also dynamic as well as thermal considerations to all of these things. That's why Fluid studies them. Fluids doesn't study it from a thermal perspective, they're studying it from a dynamic perspective. What's happening to the flow. As you can see in this one, the separation angle, as you can see in this one, the separation angle is extended considerably, and you have quite a bit more adherence of the boundary layer because the flow is turbulent than you did in the previous example where it's just laminar flow. Okay. Any questions on this? Hey, by the way, are you going to Thomas's little seminars in the evenings? Anybody going to those? So, are they? What's he doing? Playing those little movies? Yeah. I should probably get a little movie of this now that I think about it. I'm sure they got a movie of this. Are these black and white movies he's playing?
Oh, yeah.
Yeah. Yeah. No, I know. I used to have a whole collection of them. But, okay, interesting. That was all part of the people's getting a PhD. You remember the comment about, they would make all these movies of these different flows, and they use smoke tunnels. My former institution, we used to have a smoke tunnel. The only problem was the smoke tunnel, the vent didn't work half the time. So half the time you try to demonstrate something in the smoke tunnel, and the whole room would get smoky. So the only thing that really you accomplished was shortening the life of everyone that was there. And you use paraffin. I don't know if you know what paraffin is. It's like similar to candle wax, except it's in liquid form. And that's what you would heat to create the smoke. So it's really noxious after a while. The whole room gets filled with Pardon me? No. What's what I mean? If it was Yankee Candle, it'd be fine. It smelled terrible, as a matter of fact. Okay. All right. So, open your books now to table 7.7. I'm sure it's disappointing to many of you that we don't have a day or two's worth of partial differential equations to fill the boards for the cylinder flow. But we're just going to go to the empirical correlations. And to start off, we're going to redefine the Reynolds number. And the Reynolds number is going to be defined in terms of the diameter of the cylinder or the sphere, because we're going to be dealing with spheres. We're going to cover those today as well. So the Reynolds number, a function of the diameter, is going to be equal to rho v d over mu, or v D over nu. All right? And nu is your kinematic viscosity. And mu is your dynamic viscosity. Okay? D, of course, is your diameter, and V is your upstream or freestream velocity. You'll also see that written as U infinity. Okay? Now, the first correlation and the correlation which you will use as your default value for cylinders is the Hilbert correlation. Now, part of being an educated engineer is to be able to identify these correlations not by their numbers, but by their names, all right? So when you're having a casual conversation with another mechanical engineer, you can say, yes, I use the Hilbert correlation, all right? Okay? It's important. Hilbert correlation. I'm sorry, I do not have a picture of Dr. Hilbert. All right, the Hilbert correlation is the average Nusselt number is equal to C times the Reynolds number, a function of D, to the m power times the Prandtl number to the 1/3. And this is equation 744 in your text. This is the default value of the correlation that you will use for calculating the Nusselt number for cylinder cross flow. Examples of that would be a wire, a pipe, something of this nature. Okay? Now, you may ask yourself, we already know how to calculate the Prandtl number. We know how Prandtl number, of course, is a relationship between nu and alpha. We also know how to calculate the Reynolds number. Where, you say, do you find the values of this constant C and this coefficient M? So open your textbook, keep one finger on table 7.7, which should be tabbed, and go to equation 744, which will be found on page 436 of your text. This is the 6th edition. Okay? And you will see on the next page up the constants in table 7.2 for equation 744. They are based on the Reynolds number, and you'll see for different ranges of Reynolds numbers the value C and the value M. You all see that. You should have that highlighted because that's what you're going to use. Now, go back to, so let me just write that up there. Okay? Now, go back to table 7.7, and let's look at what you have. You will notice that in the Hilbert equation is the first equation that occurs with the geometry of a cylinder. Okay? You'll also notice that in the left-hand column, you will see the relationship which I just wrote on the board, equation 744. You will also notice underneath that relationship that there is a reference to table 7.2. Okay? The next column over is the equation number, 744. The next column over has the cylinder. And now let's take a look here at the values. This is an equation which produces an average Nusselt number. That is not a localized value at some point around the cylinder, but an average value around the entire cylinder in cross flow. Okay, so it's very useful in that sense. You'll see that it's based on TF, the film temperature. You'll see that it works for Reynolds numbers of a large, very large range of Reynolds numbers from 0.4 up to 400,000. Okay? And normally it's used for Prandtl numbers of 0.7 or greater, which are most air and liquid values. Okay? Most gas, I should say, not air. But most gas. Air, most air values, air is usually. Now, don't get too paranoid about that. If you end up with a Prandtl number of 0.68, it's okay. You can use that. Okay? All right. The Hilbert correlation is a very useful correlation. That is not the only correlation, though. If you look at the next one down, it is very similar to the Hilbert correlation. It is known as the Zukakis correlation, and this is equation 745. All right? Let me make, before I get into Zukakis, there's one more thing I want to say. Before we deal with the other correlations, I want to talk about non-cylindrical. This may seem a bit of an oxymoron. Let's talk about non-cylindrical cylinders. Okay? All right, say you've got something in the flow that's not circular, but it's like a cylinder. And let me give you some specific examples. Use table 7.3. So open your book up now to table 7.3, which is on page 437. This is, by the way, one of the reasons why Baron DeWitt is the #1 selling heat transfer textbook probably in the world, truth be told. Because they assembled such a mass of correlations and useful relationships in this textbook. So for non-circular cylinders, see, I didn't make this up. Well, I see. Well, I guess I did make it up. I said well, it's same thing. Non-cylindrical cylinders. Look at the different geometries you see in table 7.3. All right. If you're looking at it, as you look down, you'll see a square which is tilted, so it's like a diamond configuration as far as the flow strikes it. You'll see a square where the flow strikes it on one of the four sides, straight on. You'll see a hexagon shape, a couple of different configurations there, and then you'll see a thin plate perpendicular to the flow at the bottom of the page. Okay? Notice that there's a list of Reynolds numbers for those flows, and you'll get different C values and M values for those different geometries. What equation do you use those C and M values for, or with? Use them with equation 744, the Hilbert equation. Oh, yes, you do. Okay? So these are values that can be used yeah, you use it with the Hilbert correlation.
Oh, yeah, it's 744. Oh,
Yeah. Because when you said, I see 745 too, but it's right in the
So
title.
I didn't mean to clear off.
I thought my whole life was coming to an end. I always believed they used it with the Hilbert equation. Yeah, use it with the Hilbert equation. Now, every once in a while I do something like this. I give you an equation like this. You know how boring to write up different exams all the time and try to find out something different? So, who knows when I may not give you a hexagon shape and say, figure out the flow on that. All right. So, if you do, you should be glad that you're here for this lesson today. You'll know where to find it. Table 7.3. So for non-circular and non-cylindrical cylinders, use refer to table 7.3 and use values with Hilbert correlation. All right, now, there are some other pretty good correlations. So, other cylindrical correlations that warrant mentioning. Include the following. The first one is Zukaukas. Zukaukas is a Russian, very famous doing research in the 50s, 60s, and 70s. His work wasn't as well known to the West until later on, and this is equation 745. And you see that on page 437. Okay? Now, the equations, the coefficients C and M for this come from you get from table 773, I believe, in my book. No, I'm sorry, it's table 7.4 on page 438. Now, what is the primary difference in value of the Zukaukas equation versus the Hilbert equation? The Zukaukas equation allows for the consideration of the Prandtl number as calculated based on the surface temperature and related to the Prandtl number based on the fluid temperature. So if you go back to equation table 7.7 and look at the values, Zukaukas equation shows it has a wider range of Reynolds numbers from 1 to 1 million. It is based on its average correlation, so it gives you the average value of H around the cylinder. It is based on T infinity. Now note that, okay? While the Hilbert equation is based on T film, the Zukaukas equation is based on T infinity. So now we go back over. What values do you base on T infinity? You base the Reynolds number, the Prandtl number, and those two values. Now you have the Prandtl number outside of the correlation and inside the correlation as well. What is the Prandtl number with the subscripted S? That is the Prandtl number for the fluid properties which are flowing around the cylinder evaluated at the surface temperature. So you have the fluid free stream, you have the Prandtl number evaluated, and the Reynolds number evaluated the properties of the flow at the free stream temperature of the fluid. And then you have this other Prandtl number which is in there, which is in that ratio, which is based on the surface temperature. That's the way Zukaukas did it. Typically, this correlation is considered to be a better fit when there is a significant significant temperature difference between the surface that is being heated or cooled and the fluid which is flowing over. So if you get a significant delta T, you're better off, according to common application, to use the Zukaukas equation rather than the Hilbert equation. But let me tell you something, and then I'll answer your question. In general, I go back to what I said. Don't worry about this. What is the default value in this course for calculating cylinder crossflow? Hilbert. Okay? So just use that. If I were to write a problem and say, Zukaukas equation, there's a big temperature difference in this, use the Zukaukas equation to solve for the correlation, then follow the instructions in that problem. Ariane?
For equation 7.45, you said it's based on the surface temperature or ambient?
No, I said the Prandtl number, look at equation 745 carefully.
No.
We'll look at somebody who does that. All right. You will see that there is the Prandtl number in there in two forms. There's a Prandtl number with the subscript S. That's the Prandtl number which is based, the fluid properties, based on the surface temperature of the cylinder. The other Prandtl number and the Reynolds number are based on the average, or on the temperature of the free stream velocity, T infinity. So you don't use T film in this correlation.
What's the N?
These are values, if you look in, right underneath equation 745, it says, if the Prandtl number is less than 10, N is equal to 0.37. If the Prandtl number is greater than 10, N is equal to 0.36. Okie dokie. Okay, so that's the Zukakis equation. The other equation, which is kind of near and dear to my heart, because I never knew Churchill, but I used his work years ago, is the Churchill equation, or Churchill correlation. This fellow was a very, very busy guy. And he came up with literally dozens of different correlations. He did all this work and he came up with this curve fit method, which is why this thing looks with all these different exponents. What he did is he graphed all these curves. He took all these data and he graphed all these curves on log graph paper. Now you may not know this because you live in the digital world, but before you had all the calculators. Calculators weren't around all the time. The first calculators, the little things that we are all accustomed to now, started coming out in the late 70s. And when they did, the first ones were really, really expensive. They were like $100, $200. They could add, multiply, and divide. Other than that, we had to use math and slide rules and things, and books that had trig formulas. That's how it used to be. But to get these types of relationships, you get log graph paper. Now, how many of you have ever seen a log graph? All right. Well, the thing about it is, if you use log graph paper, you can plot things, and then you fit the curves to them, and it comes out with different exponents. All right, raised to a certain power. It's kind of neat to do this. This is what Churchill did. I can just imagine what his lab was like. All these log graphs. You draw all these lines, fit curves to them. In those days, you actually fit curves. You have little dots all over your map, okay? Or your log, and you take your ruler and you go in there and you fit the curve. You can also do it mathematically with log graph paper by taking a logarithm of all these things, and you do that as well. And you can come up with the slope of the curve, which would be your coefficient c, and then exponent. Yeah, that's what it is. So anyway, the Churchill equation is equation 746. And I'm running out of time. I always loved this class, but I seem to run out of time. All right, this is what you're going to do. You're going to work problems. I can talk until I'm blue in the face on this stuff, but the real way to learn this stuff is to work problems. So that's why I gave you 4 problems to work. Okay? All right? Now, before we leave, there's one more thing I need to talk about. Spherical correlation. This is not a hard choice. There is only one correlation for spheres. That's the Whittaker equation. And that's equation 748. And you will see that in your book. Notice that it's an average value as well. That is, T infinity for the properties. And lest I forget, let me just do one more thing real quickly before you leave. In a minute, and that's about all it will take. Let's officially put the film temperature up. I have been talking about it a number of times. It's in your textbook and you're reading, but it's worth writing up here. Film temperature, we have flow over a surface. Let's draw for a moment a flat plate. We have the formation of the boundary layer, we'll have two temperatures here. We'll have T infinity out here, and we'll have some T surface. That's typically the case. You notice that we've been assuming all along that these are isothermal surfaces. Okay? One of the reasons why your correlations, why your didn't work out quite as well for the transient ball experiment is that the surfaces aren't isothermal, they're constantly changing. But the film temperature is defined, TF, as being equal to T infinity plus TS divided by 2. And this is the value that you will use more often than not for most correlations to calculate your fluid properties. Okay? You have to look at the relationship, the requirements, the correlations, these empirical correlations which we use are based on different techniques, either using this, sometimes using this, sometimes using this, as I've been describing. So you need to look at what's required in the correlations before you use them and ensure that you comply. That's the film. Any questions? All right, you got 4 problems to do, due on Monday. You have a wonderful weekend, holiday weekend.